So in the first half of part 2 of this section, we looked at the disk method, which was a particular example of the method of slicing which we had been using to compute some volumes. And now what we want to do is we want to generalize and improve upon the disk method a little bit. We're going to start off by looking at the region R, bounded by the curves y equals root x, y equals root x minus 1, x equals 10, and the x-axis. Compute the volume of the solid formed by revolving R about the x-axis. So very similar to one of our, this is going to be a solid of revolution. It's very similar to one of our disk method problems that we've seen so far. But we want to take a look at what this region looks like before we go about blindly applying some disk method formula. So if I have my axes here, I know these two functions live in the first quadrant. And I'm looking at the curve square root of x as one of the curves. So let's draw that. That is a function whose graph we should know. Looks something like this. Square root of x minus 1 is going to be a translate of square root of x, 1 unit to the right. So if here's the square root of x, I want to translate this 1 unit to the right, which looks something like this. So this will be y equals square root of x minus 1. I have x equals 10 as one of my bounds. So here's 10. And I have the x-axis as the other bound, so the black vertical line here. So the region that I must be looking at revolving then is this purple region, which I'm shading here, all the way up to that blue line there. All right, so this is similar to one of our disk method problems in that, well, we're taking this thing and we're revolving it about the axis somehow. But the difference is that our region R here is a region that's bounded by two curves rather than bounded by one curve and the x-axis, except for part of the domain. So let's think about what's going on here. Here's x equals 1, and between the x values of 0 and 1, the region that I'm looking at is in fact the region bounded by a curve in the axis. So we can find the volume of that piece using our disk method. So let's go ahead and do that. We know that volume is additive, meaning that if you can split up a solid into two different pieces, then what you can do is, in order to get the volume of the whole solid, you add up the volumes of the two pieces. And here, maybe what my solid looks like is some kind of sideways cup. I have some kind of a couple of circles here on one end, and they go down and they kind of meet up here at the origin. And this is, it has some thickness to it, but it's hollow in the center, except for some little piece kind of right at the end there. So with this solid, what we want to do is we want to recognize that for the x values between 0 and 1, a cross-section is going to look like a circle. So one of these cross-sections that we're forming is going to be a solid circle. And its area, as usual, is going to be given by pi times its radius squared. Its radius here is the y value on the function y equals square root of x. So the reason that we're looking at that is that one of these cross-sectional circles here intersects the xy plane as a vertical line here. We're thinking about x values between 0 and 1 here. So its area then is going to be pi times its radius squared. Its radius is the square root of x, and so its area is going to be pi times root x squared. But if I were to draw a different cross-section, maybe I were to look at the cross-section formed by a plane to the right of x equals 1. So here I'm looking at 1 less than x less than or equal to 10. Then the shape that I get is not a solid circle, rather, or not a solid circle, but rather it is going to be kind of a hollow circle. It's going to have an outer radius and an inner radius, and the way it intersects this solid is that it's solid between the outer and the inner radius there. So to compute the area of that disk, what we want to do is we want to take pi times the outer radius squared. We want to take the area of the full circle. So we want to maybe think about what's the area inside this outer circle, so including all of the stuff in the center. And then we want to subtract away the area inside. So the radius of the full circle is pi times the outer radius squared. The outer radius here is given by the function y equals square root of x. And so the outer radius here is, the outer radius is square root of x. So the area of the full circle, without the hole removed, is pi root x squared. But we want to remove the hole here, and so we want to take away the area of the inner circle. The inner circle being this gap here that we're missing. So in order to remove the area, we need to subtract away pi times the radius of that circle squared. And the way that we take away that area is it has radius according to the y value of the smaller function. That smaller function being root x minus 1. So its radius is root x minus 1 squared. So we have these two different portions of the solid here. We have kind of the base, which lives between x values of 0 and 1, and that corresponds to this region here on our picture. And we also have the remaining solid here, where we have some kind of, this looks a lot like a washer, some piece of hardware, though the washer, which is hardware rather than like your washing machine. And so we're going to call this the washer method because we are thinking about these cross sections here as washers. So with the washer, we said the cross-sectional area was the pi times the radius of the larger function squared minus pi times the smaller function squared. And so what we have then to compute the volume of this whole thing is we want to integrate these functions according to their domains. So the cross-sectional area between 0 and 1 has its own formula. So integral from 0 to 1, we want to integrate pi times the square root of x squared. Well, square root of x squared is x. On the interval from 1 to 10, we want to use our other cross-sectional area formula, which is pi times root x squared. Well, root x squared is x again. But this time we want to subtract away pi times root x minus 1 squared, i.e. x minus 1. This is a nice integral for us to compute. This is going to be, we know that the integral of x is x squared over 2, evaluated from 0 to 1. Over here, we can recognize this. We could expand this out, actually. If you simplify some of the arithmetic here, you get a pi x minus a pi x, which is 0. And then you're left with a minus pi times a minus 1, which is a plus pi. So this is just the integral of pi. And I know the integral of pi is pi x, evaluated from 1 to 10. Great. So now what we can do is we can actually evaluate this first term here. If we evaluate at 1, is going to be pi over 2. If we evaluate at 0, we get nothing. The second term is going to be, if we evaluate at 10, 10 pi. If we evaluate at 1, 1 pi, or just pi. And now we have pi over 2 plus 9 pi is going to give me 19 pi over 2 for the volume of this solid. All right, so a little bit complicated, in part because we had to integrate, we had to use two separate cross-sectional area formulas, and also in part because we had this washer show up rather than our usual disk. But once we worked through those different possibilities, we were able to compute the volume of this solid fairly reasonably. So let's formalize this washer method here, and then later we'll see a couple of examples. So the washer method says let f of x and g of x be continuous non-negative functions defined on an interval ab. Remember, this means we want them to be above the y-axis. We also want them to be continuous so that we can make sure that we can integrate them. We want R to be the region bounded by the graphs of y equals f of x and y equals g of x, and we want to find the volume of the solid formed by revolving R about the x-axis. So as a reminder, here's kind of the picture that we're looking at here. Here's A and here's B. We have some function f of x, which is above the axis. We have another function g of x, which is also above the axis, and maybe they intersect, maybe they don't, we're not really sure. And the region R that we're looking at here is the region that's bounded by these curves. What we want to do then is we want to integrate, so again, kind of if we rotate this thing about the axis, if we rotate R about the x-axis, we're going to get some shape or some solid whose cross sections are these washers. And sometimes these washers will look like blue outer radius and green inner radius. And for those functions, or for those portions, we want to integrate f of x squared minus g of x squared, or pi f of x squared minus pi g of x squared, because pi f of x squared represents the radius of, or pi f of x squared represents the area of the blue circle, and I want to subtract away the area of the green circle, which is my pi g of x squared. On the other hand, sometimes I have a green outer radius and a blue inner radius, which means that I want to be looking at pi g of x squared, area of the green circle, minus pi f of x squared, which is the area of the inner circle. So in order to account for the fact that I always want to be taking pi times the larger function squared minus pi times the smaller function squared, I want to integrate here from a to b the absolute value of the difference of the two. So this is the way that I guarantee that I'm taking the larger minus the smaller. And there's a slightly simpler way of writing this formula. We can factor the pi out of the absolute value. So this is going to be a to b, and you can factor the pi out of the integral as well if you want. F of x squared minus g of x squared dx. Great. All right, so I'll give you the opportunity to work on a couple of the next examples before the next video.